Hello friends, this video on chemical bonding part 30 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure you have watched part 1 to part 29.
Now you must be wondering, why did we do so much electronic configuration? What information we are getting from electronic configuration? So let's see this. The molecular behavior can be predicted from electronic configuration. Stability of molecules, the bond order, the nature of bond, the bond length, magnetic character. All these things we can find using electronic configuration. We'll explain this one by one. All these things we can find if you know the electronic configuration of a molecule. So if let's suppose my Nb is the number of electrons in bonding orbitals and Na is my anti-bonding orbitals, then my molecule is stable if my bonding is number of electrons in bonding is greater than number of electrons in anti-bonding. So if my bonding electrons is greater than anti-bonding electrons, my molecule is stable. Quite reasonable also, because I told that bonding has lower energy, anti-bonding has higher energy. So if I have more and more electrons in the bonding orbitals, that means my system is pretty stable, right? And if it is stable other way around, if my anti-bonding electrons count as more than bonding electrons. Bond order, as I told in case of Lewis definition, the bond order was nothing but the number of bonds. But in this case, the bond order is nothing but 1 by 2 or half the difference of the number of electrons in bonding and anti-bonding orbitals. Bond order is nothing but 1 by 2 into Nb minus Nb, where Nb is nothing but number of electrons in bonding electrons, C, B for bonding, A for anti-bonding, minus Na, that is number of electrons in anti-bonding. So here also positive bond order means molecule is stable, and the negative means negative or zero means the molecule is unstable. Correct? Because we told that if it is positive, that means my bonding molecule will be number of electrons in bonding orbitals will be greater than number of electrons in anti-bonding orbitals. So we talk about nature of bond. So integral bond order of value 1, 2, 3 is generally for single, double or triple bond, right? This is generally something which we learn in the classical concept, but we have seen the resonance and all, right? In resonance we have something called, we get 1.5 as a bond order. There we talk about the resonance, correct? So if we get bond order is 1, we say it is single bond, 2 double bond, 3 double bond. If it is 1.5, say it's something called resonance. When you talk about bond length, since till now we have just got the bond order, how to get the bond length? So the theory says that the bond order can be taken approximate measure of bond length. That means we say that bond length is inversely proportional to bond order. So I know the bond order, higher the bond order, lower the bond length. And that is something which we have seen in the earlier theories also. So for double bond, the bond length was less. For triple bond, the bond length was all the more less. Right? So same thing here. So with the bond order, we can have a fair idea of the bond length also. So bond order is something which we can easily find using molecular orbital theory. Magnetic nature is something which we can easily find. When I started this theory, I talked about oxygen being paramagnetic, and it's difficult to tell it is paramagnetic by the earlier theories, but this theory helps us to find the magnetic nature. For example, oxygen molecule, right? We'll tell you how to find this. So it says that if all the molecular orbital in the molecules are doubly occupied, it is dimagnetic, and if one or more molecular orbital are singly occupied, it is paramagnetic. So in case of its paramagnetic, it will be attracted by magnetic field. If it is dimagnetic, it will be repelled by magnetic field. Correct? We'll take some examples where we'll explain all the properties once again, right? So we'll start with hydrogen. So hydrogen molecule is nothing but my 2 hydrogen atom, and hydrogen, my electronic configuration is 1s1 for hydrogen atom. So I have 1 atom here, 1 electron here, 1 electron here, right? So if you fill this is 2 electron here. So now if you see hydrogen, everything is filled. Let's find the bond order first. Bond order is nothing but 1 by 2 into number of electron in bonding minus number of electron in antibonding. So how many electron in bonding? 2. Antibonding 0. So this becomes 1. That means there is a single bond, and which you can see that hydrogen has a single bond. Correct. Also, there is no unpaired electron. All the electrons are paired, so it is dimagnetic. Let's take helium. So in case of helium, we'll have the structure. So helium is my helium molecule is nothing but 2 helium atom. So helium atom, my electronic configuration is 1s2. So let's put 2 electrons here and 2 electrons here. Correct. So we'll have 4 electrons. Let's fill 4 electrons in this fashion. So what is the bond order? 1 by 2 into number of electron in bonding minus number of electron in antibonding. So this becomes 1 by 2 into bonding electrons, there are 2. Antibonding, the star is 2. That becomes 0. So bond order is 0. That means it is not stable and doesn't exist. Correct? Very simple. There is no point in finding magnetic nature. Let's take beryllium. So for Be atom, my electronic configuration is 1s2, 2s2. Correct? So let's put 1s2, 2s2 here, 1s2, 2s2. Correct? Let's fill it. 4 electrons, all filled. 4 electrons, all filled. Let's find the bond order. 1 by 2, number in bonding minus number in antibonding. How many electrons in bonding? 2 plus 2, 4, right? These 4. Antibonding, the remaining one, 2 plus 2, 4. This also gives 0, that means it doesn't exist. Pretty easy. Lithium, let's see if lithium to exist or not. And if it exists, what is the what is it is paramagnetic or dimagnetic? Let's see this. So for lithium, it is 1s2, 2s1. This is my lithium atom electronic configuration. So let's put this 1s2, 2s1, 1s2, 2s1. So now let's put the values. There are 4 electrons. Put the 4 electrons. 2 electrons, both will be here. Let's write the bonding order. 1 by 2 into n bonding minus n anti-bonding. How many bonding? This and this. So 4. Anti-bonding, the remaining one, 2. You get 1. That means it is single bond. Correct? It is stable. And what about the magnetism? It is paramagnetic or dimagnetic. You see, there is no unpaired electron. So it is dimagnetic. Correct. Let's take for the carbon. So carbon is 6 electron in the carbon atom. So 1s2, 2s2, 2p2. Right? This is the carbon atom. So let's put here 1s2, 2s2, 2p2. Here also same thing. Correct? So let's fill this 4 electron. 4 electrons. Now we have again 4 electrons here. Right? So 1, 2, 3, 4. Correct? So let's find the bond order. 1 by 2 Antibonding minus bonding minus antibonding. How many bonding? This is bonding, this is bonding, and this is bonding. 2, 4, 8. 8 minus antibonding is 2. With this 3. Correct? So that means it is a carbon-carbon triple bond. So there is a mistake here. 2 and 2, 4. It is 4 here. So 8 minus 4 by 4, it is 2. That is double bond. Also it is stable because it is greater than 0. And there is no unpaired electron, so it is dimagnet. Correct? Let's take oxygen. Oxygen atom has electronic configuration of 1s2, 2s2, 2p4. Let's fill this. 1s2, 2s2, 2p4, 1, 2, 3 and 4. Similarly here we'll fill the same values. Correct? Now let's write this 4, fill this 4, 4, fill this 4. Now we have 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Let's write the bond order for this. 1 by 2 and bonding minus antibonding. How many bonding? 2, 4, 6 and 4, 10. 10 minus antibonding is how many? 2, 4, 6. Right? So you get 2. That means there is a double bond. What about the magnetic character? I can see the unpaired electron. Right? So it is paramagnetic. Since unpaired electron are there, so it is paramagnetic. Correct? Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.